Give me a soft copy, that's fine, but if you didn't, then I need more evidence. I can't create you maybe say, well, I got 95% of my intervals. Yeah, I believe you. Show me. You know what I mean? So I need to have that evidence in your homework. So just be a little bit more careful. No, you did plenty. I only needed 10 or 15. That's plenty. Intervals. But I just need some evidence. So I think I'm going to warm up this computer a little bit, see if a couple other people show up before we get started. I apologize for the delay. Okay.
Still broke.
Okay, that's fine. I'm sure it's still broken. I'm not worried about that part. I'm worried about whether the light will come on eventually. You can? I didn't know that. Okay, I might have to do that.
I changed the batteries in that, so
I think it came on. Okay. So, let's see. Today we have a lot of things. There was a little bit of cleanup on Chapter 3 I was going to cover. Just, though I have not assigned any problems on that material, I believe. Joint confidence intervals, or joint confidence region. I thought maybe you should at least see hidden extrapolation. We should talk about that. And standardized regression coefficients, we need to talk about that just a little bit. So I want to cover those, and then I want to get into residual analysis. And the last thing, which I don't know if we'll do today, is normal probability plots. Normal probability plots is kind of a separate issue that doesn't play a very big role in this course. But since he's entered that topic, I'm going to try to do a little bit better job than the author does on this one. Okay, and normal probability plots.
Is this like testing for normality? Or?
Yeah, testing for normality.
Okay.
Testing for normality, or whether actually, and then the regression application takes a slightly different tone because you can't test for normality of the residuals. In fact, what happens is that you can argue that the residuals won't even be normal, okay, because you've done these parameter estimations. So even if you had the normality assumption with the actual residuals, independent normals, after you do the estimation, perhaps, the estimated residuals are no longer normal, okay? And anyway, normal probability plots are kind of hard to decipher. What's going to happen is that normal probability plots are going to be useful for detecting outliers. But in general, they're just going to be kind of another tool in your bag which you're just going to maybe look at now and then. But it's not going to help you that much. But I thought we'd go over normal probability plots to clear the air about them, because Excel doesn't do a normal probability plot, even though Excel has that under their regression tool. It says normal probability plot and a little check. It doesn't give anything close to the right answer. Okay? And so that is a very weak part of Excel. And I just thought I'd point that out. I don't know why that hasn't been revised.
Because too few people use it to justify the cost?
Perhaps. Maybe Google will do better. I don't know if Google is going to have everything Excel has. If they do, they better be better. Okay. So another point that I wanted to make was that we have changed the website address. Even though you'll probably be redirected from the old website, the new website is www.uccs.edu/gmorrow. I guess there's a tilde there too, but I guess it doesn't matter whether you put it in or not in order to get the actual web page to come up. Okay? It does not matter. Okay? So this is a new web page.
It's not on MathWeb server anymore.
No, MathWeb server is about ready to die. Okay? If it hasn't been dead yet. But it will have been forwarded. It should have been. I haven't checked whether it has been. It's not. It should be forwarding.
It did.
It did for you?
Had a refresh.
Okay, well, one person got it to forward. Okay. All right. So, let's double check to make sure the actual picture would come on if I wanted it to. Yes, it. What? That's some kind of input thing.
Oh yeah, you're on the wrong input.
Video.
The podium connected is on the switch to laptop or
Or Podium. It's got to be on Podium, right?
There it is.
There it is. Okay.
One more time.
What is that little thing?
It's on
Okay.
the picture's being muted or not.
Muted picture. That's a good one. Okay. Okay. So I did mention at the beginning of class that I didn't turn your homework back yet, but I did have a couple comments, and that if you did not submit some evidence of the confidence intervals for that problem 217, then you're welcome to submit it by, later today or on the email or something like that. Just give me one page of Excel or something to show me what you did or something, or just give me your whole 217 if you want. Because I'm finding that people didn't actually show me what the confidence. They said, 100% of my confidence interval is contained. Okay, if you showed me actually what the intervals looked like, that's fine. I don't have to read the formula because I can figure out what the intervals look like if you're doing the right thing. Okay, I don't have to know every calculation you made. But I need evidence. I actually need to know what the intervals were. Okay. So just give me enough evidence that I, as an intelligent person, could figure out what you were doing. All right, you don't have to give me every last calculation, though I would like that too. If you actually told me the formulas you used and so on, that would be great on a hard copy. I just don't want to sift through your soft copies, okay, forever and ever and ever. I know it's the wave of the future, but I'm still an old dog, okay? All right. And I would email it back to you with all the red ink and so on in Excel, but that's, at this point, it's just a little too time-consuming for me. Okay. Why don't we start the lecture? Are there questions? Any questions? Okay. Okay.
Get my wording right.
Okay.
Is it okay that show variability is good, but then show, I don't know if I have an error in my word.
Okay. This is on problem 3.5 or something?
Yeah, it's I showed for test significance that at least one of the regressor contributes significantly to the model.
Yes.
Then I was down calculating, calculating the statistic on beta 6.
Yes.
And found that it does not, one of them does not contribute to the model. So I don't know if I have an error or...
That's correct. One of the T statistics is not significant.
Okay.
Okay. After you fit the size of the engine, the number of carburetor barrels or whatever is not so important.
Okay.
I think that's what it comes out.
And yet there's a dramatic increase in like the R squared value, isn't there?
Right. That's what I'm saying. The R squared shows...
How much?
It's not a lot. That's right.
Yeah, if there's an increase in R squared, fine. There's always going to be an increase in R squared. It has to be when you add another regressor. How much, though? And so how much, you'll see that maybe it's not that much. Okay, R squared is difficult to interpret.
Okay, so if we originally concluded that it was meaningful, and then we find this thing back in F or whatever it was, then can we go back and then just state, well, maybe it's not as meaningful as we thought?
How did you think it was meaningful?
Because I had an increase.
Okay. Yeah, well, now you learn how to read the charts.
Right.
Okay, so let's... Yeah, I think you got... let's see, what are the two R squareds that you're getting?
R
squared was just simple linear regression? You said our regression on x1 alone give you what R squared?
For the new model, 0.787. For the old model, 0.772. So.
That's hardly any change at all.
Oh.
So I don't see that's a significant increase.
Okay.
So it always has to be, it has to increase. See, that's the point. It has to increase when you add more regressors. R squared will go up forever and ever and ever. Just throw in garbage and it'll go up. Okay, but it won't go up very much. All right.
Cool. That's what it is.
Okay. Because it's SSR divided by SST, and the regression sum of squares is what is accounted for by the regression model. You can always account for more and more and more just by putting in thousands of useless regressors.
So how does that
Okay.
that, like R squared adjust?
As long as the computer doesn't fry after the 1000th regressor. Okay. Yes, go ahead.
So the adjusted R squared also improved.
Adjusted R squared is a little bit more difficult to interpret. I just skipped it. Okay, I just skipped talking about that. But they have some discussion in there. I'm leaving that to you. I'll make some comments about it next time if you want. Okay. Maybe we should look at it now. You have a question about our adjusted R squared? Yeah, so that, well, there was some effect of the number of carburetor barrels. The T statistic was not 0, right? It was something like 1.5, okay? Which means there's something going on there. You know, there's a little bit of effect. But I think if you could also get some visual data. Today we're going to talk about, if we get there, we're going to talk about partial regression plots. So what you could do is you could get a feeling for, a visual feeling for whether that second regressor is useful. They show you a picture of that on page 148, where they have a 2-regressor model for the delivery time data. These are partial regression plots. This is going to be another way to study this. Unfortunately, I don't have the text online, so I can't put it on the screen. But on page 148, there are 2 plots there. What are those things? Those are called partial regression plots or added variable plots, which we'll explain a little bit later. And they're in the notes today. What you do is, okay, in the delivery time data, it's very similar to this gasoline mileage thing. Okay? There were 2 regressors. One is the number of cases that the shelving person or whoever it is, delivery person is going to stock, okay, of the soft drink. And then the distance they had to travel with these cases, apparently, is the other variable. It's comparable to the carburetor barrels, okay, in some sense, almost exact kind of feeling of how the 2 variables contribute. What this is showing is, this is a kind of a picture of how when x1 is added after x2, okay, if you've just accounted for the second regressor, okay, and then you added x1 into the model, then and the t statistic that you get in the Excel output for beta 1, all right, equal to 0. H naught beta 1 equal to 0 gives you a t statistic, right? You have a bunch of hypotheses here. H naught beta 0 equal to 0, you have H1 beta 1 is equal to 0, and you have H naught beta 2 is equal to 0. Okay? In your problem 3.5, I think the t statistics were something like, in absolute value, were something around 8 and 1.4. Okay, for these, and this was something like 23. Okay? It's outrageous. Or 22. Okay? Something of that order, ilk. Okay? So, if you fit x1 after x2, okay, then you're testing whether beta 1 is equal to 0 after you fit x2. That's actually what this t statistic tests. Okay? Fitting x1 after x2 and the intercept. Okay? So, tests fitting x1 after x2 and intercept. And that goes for all of these t statistics. So this is actually test the intercept after you fit x1 and x2. Okay? And this tests fitting x2 after you fit x1 and the intercept. Okay. So what this gives you, though we haven't discussed what these partial regression plots do, is that this kind of gives you a visual feature of how important x1 is after x0 and x2. Okay. Right, after the intercept in x2, that is. Okay. And this shows whether there has to be these dots should be going through the origin and have a slope. Okay. Roughly speaking, if the variable is important. Here, this clearly that's the case. In this second plot, it's not so clear, right? Is there much slope there, or is it just kind of an amorphous mass and then plus error? All right. So that's kind of what's going on with your second regressor. There's a little bit of an effect. Okay? I believe you could do the partial regression plots for your problem if you know once you learn how to do them, but it's a pretty easy formula. Okay? There's going to be visual techniques for studying these variables. Okay. So that's by way of where we're supposed to get to today. Sort of. Okay, so we have a long way to go. All right. Any other comments about what the ANOVA table and what I discussed this last time, though I didn't actually write this down, right? This is what you're supposed to be knowing. And then there's corresponding F tests. Right? So if you actually get what is the F? Let's go ahead and let's see. I will have to ask you for numbers. I'd have to do two numbers. We could actually test this. If I square this, I get a certain F ratio. Okay. What would I have to do? How could I write that this t squared is an F ratio? Right, this, if I call this t naught equals 8, roughly. What was it, 8 and something? Anybody else have their hand out? It doesn't matter. How could I write the square of this as an F ratio? That was from the last lecture. Okay, so what would it be? SSH equals SSH divided by sigma hat squared. Okay, and this is divided by 1 in this case. Yeah, so the F corresponding to this hypothesis is this. What is SSH though? So this H is that H. Okay? So what is the SSH? No, it's a difference of SSRs. Okay? This is an SSR, or we can do it in SS res. This is the difference of SS res is SS res of the reduced model minus SS res of the full model. So you'd actually have to do, and then divide by sigma hat squared. This is the full. Okay? And this was divided by 1 then, because there's only 1 degree of freedom in this hypothesis. So I'd actually have to do the regression. What is the reduced model? That's when I take beta 1 out. So I only do x0 and 2. I mean, the intercept in x2. So I'd have to do a regression. All right? Of that. Okay? So if I actually do that, let's just see. Let's just go ahead and do the calculation and do it. Okay? So I want to make sure I get that 8. Okay? So I'm going to go ahead and print the printout. There's only one hard part of problem 3.5, and that's the last part, part F. I'm hoping everybody's realizing that. But let's just go ahead, and the interpretation was part of the problem. Okay, so the what? Oh, there's the next part G. I forgot about that. I didn't even look at it. So don't forget to go to the next page in 3.5. There's 2 last hard parts. Okay? Yes. The other lights, too. Is that better? The front one is the bad one. Okay, there we go. Okay, so I don't need this data for problem 3.8, but let's just go ahead and so I can look at this stuff. There's the data for problem 3.5. So let's go ahead and find SS res full first, and then MS res full, which is the sigma hat squared. Okay, so let's just go ahead and regress y on both variables. So what do I need? Tools, data analysis. Hey, it's still there. Good. Okay, regression. Everybody with me on this? I'm sure you've done it a million times. Input range. I'm going to put the label in this time too. Okay. X range. Okay. Labels. Confidence level. I'll just skip that. Output range. Let's keep it on the same page. Residuals. I'm not going to need them for this particular one, so I'm just going to skip it. Okay. Output range. Let's put it right here. Okay. So there's all the stuff plus the extra 2 confidence intervals that I don't need. I always clear that business. Okay? Because I don't know why it's there. All right. So there are 32 observations. Let's see. SS res was 263.235 and MS res was 9.077. Okay? So what we had was that SS, I just write it down this way. SS res was a full model. Okay, came down to be equals this guy. Okay? All right. Then I had MS res, sigma hat squared.
Why does it you need?
I need that for the denominator, for the F ratio. Okay? That's equals to this. All right. Then I need the reduced model, right? And I notice here that the T0 statistic, by the way, T0 for H1 equals 0. So H naught beta 1 equals to 0 has a T statistic is equals to that negative 8.66. Okay.
Now, so that was using how many degrees of freedom on that t-test?
That's 29 degrees of freedom. Okay, residual. Okay. So now I'm going to go ahead, and there's 29 degrees of freedom in the sigma hat squared. That's the sigma hat squared full. Okay. I can put when I put sigma hat squared, I mean the full model sigma hat squared. Okay, because I'm going to get another sigma hat squared. I should put the hat in here. Forgot about that. Okay? Yeah, that's better. Okay? That means full model. Let's put it this way, FM, so everybody's full with that. Okay, now we need another regression, right? Y on X6 only, right, with the intercept. So let's go ahead and do that. tools again, data analysis. So this is the way you do it. The poor man's way to do it is, maybe the rich man's. You just go ahead and do all the calculations again, right? Because it's just at the flip of a button. Okay? I don't have to do the special calculation that they show in the formula in the book with x prime x inverse and whatnot. All right? Though I could. And we'll have to do that for parts F and G anyway. Or you're going to have to do some x prime x inverse stuff. But let's just go ahead and finish this problem. Okay? So then I get, for data analysis, the regression again. Okay, the y is the same. The x now is different. I just need one column, and it's on x6 this time. So I'm going to, right? So I'm going to fit x1 after the other one. Labels, output range, better change that to down here. Okay. Did I get it right this time? Oh, it was on K30 already. That's fine then. Okay. Now, here's the summary output. I hate these things. So what do I have? Let's see, I'll just pull it up here. I have SS res now. Wow, it's much different. Okay? So now the SS res, I guess there's room to put it here. SS res reduced model. Now, that's equal to this one right here, 944. Okay. Get this out of the way just a little bit. Okay. And that's all the other number I needed, right? That's the only other number I needed. So when I take the difference of these and the SSH is the difference of them. Equals the bigger number minus the smaller number.
So we always do that so we can use a one-sided f-test or no?
This is f-test is just f-test just is f is a non-negative variable, so the tail, basically the tail of the f is going to correspond to two tails of the t. The upper tail of the f corresponds to two tails of the t. There is an upper tail and lower tail of the f statistic, but the f statistic is asymmetric. All right. So an f1 nu equals a t nu squared. Can you read that over here? I guess I could write that on the just right on the screen. So the theory is the f sub 1 numerator degree of freedom and nu denominator degrees of freedom is equal to a t random variable of nu degrees of freedom squared as a random variable. It's not the t squared. Well, the whole thing is squared. Hope you can read my mathematics here. Okay? It's a t random variable squared. Okay? As a random variable, that's what it is.
Where nu is still n minus p?
Nu is n minus p, or whatever nu in this particular formula. Right? This is for any nu. But for application, of course, nu is n minus p, which is 29. Here, nu equals 29. All right. So that's the SSH. Now I just want to check, and I'm sort of trembling here whether I got it right, whether SSH divided by sigma hat SSH divided by, so now the F statistic, which corresponds to this beta 1 equal to 0, is F naught equals SSH, which is this number, equals, well, I already wrote it on the board. Is everybody clear? It was SSH equals this number divided by 1, okay, all then divided by sigma hat squared, which is this, okay? I don't need that many parentheses, but I did anyway, okay? SSH divided by 1 divided by sigma hat squared. Okay, it's pretty clear with all the little things on the screen now, right? So, enter that, and hope that that's equal to t squared. 75, that looks right. If I square this number, right, it should be 75, right?
Well, I have a question. Like, why are we using sigma hat squared from the full model, whereas sigma hat squared under our condition that beta 1 equals 0, shouldn't it be the one down here?
No,
Why not?
because you need independence.
Okay.
That's not independent.
I thought, okay. Cool.
Okay, it's fitting beta 1 after. Okay, yeah. But that won't be independent of that one.
Okay. See, I thought we used that.
SSH will not be independent of the sigma reduced model squared.
Okay.
Because you changed SS res a lot too, right? When you changed, okay, so you have to take your best estimate. Your best estimate of sigma squared is with both variables in the model anyway. Okay, remember that idea of the key? You had some key variables and then a bunch of junk. Okay, well if you don't put in one of the key variables, all right, then your bunch of junk doesn't have variance sigma squared anymore. Okay, it's not even have zero mean. Okay.
I wasn't sure because we were under the assumption that beta 1 was 0.
Yeah, but no, the independence is the problem. Okay. So equals this number squared, and you get the 75.00296. So there's the numerical evidence, okay, that really the t squared is equal to the f test here. Okay. So anyway, it's Should I explain that some more? Let's see. This is SS res is all right.
And that was using a two-tailed T, where it's just using the one tail of the F?
Yeah. So the two tails of the T, or the one tail of the F, okay, and the p-value was 10 to the minus 9, okay? So what I have is that the probability, if you want this written down, the probability that an F random variable of 1 and new degrees of freedom is greater than 75.00296 is equal to, that's an F random variable, bigger than this F naught value that we found, that probability is equal to this number here, 1.55 times 10 to the minus 9. All right. That's the probability statement. The probability that the absolute value of a t random variable is bigger than the absolute value of minus 8.66 is equal to the same number. So that's the two tails. That the absolute value of a t, I put a capital T, t sub new, okay, an absolute value bigger than absolute value of the negative 8.66 absolute value equals the same thing, 1.55 e minus 9. Okay? So those are the p-values. The probability that that's the two tails. It's a two-tailed probability. Is everybody together with this now, with those the interpretation of the tables?
Go through it, repeat those t-stats?
No.
Okay.
No.
Just for-
You could if you wanted to. Put in t dist, x degrees of freedom in tails, okay, 8.66. I guess, do I need more digits? 66042. I'll just put 866 and see what we get. Degrees of freedom was 29, right? In tails, I'm saying 2. Okay, here it actually gives you the option of how many tails on t dist. T dist is different than t in. T in is what you're using to calculate these things, right? Okay. So there's your p-value calculated. Okay. These are kind of small p-values, so there's no need. Once you get a t-statistic more than 3 or 4, well, 4 or 5 anyway, okay, then they're astronomically small p-values. Okay. So we're looking for basically t's that are between, it's like minus 1 and 1, which means you just basically there's no contribution to the model, or t's that are 4 or 5 or above. Okay? And somewhere in between is kind of no man's land, like you sort of had in here. Okay? Whether are you going to include in the model or not. All right. I think that's it for this discussion, right? For now. Okay, let's go back to the development. We want to get to this residual analysis. Okay. Okay. Let's see. What do I want to say? Well, okay. I think I won't go through the calculation, but maybe you'll believe the following. I just want to make a couple comments on joint confidence region. And because Shane was asking about simultaneous confidence intervals and so on last time. How would I get a simultaneous confidence interval? For, let's say, beta 0 and beta 1 in simple linear regression. In simple linear regression. Because when I do a confidence interval, I didn't actually put this in the notes, but let's just go ahead and look at it. If I get a confidence interval for beta 1, which you have done for me, if we get a confidence interval for beta 0, those are individual confidence intervals. And so I don't know simultaneously with 95% confidence that both beta 0 is in its confidence interval and beta 1 is in its confidence interval. What could I say if I had two 95% confidence intervals and I was 95% confident that beta was in its home and beta 1 was also home? Okay. That the both would be home.
90%.
90%. Very good. That's the method. Okay. That's it. Okay. I take the alpha and I take the error probability and multiply it. Okay. So if I want simultaneous 95% confidence intervals, I have to take the alpha and divide it. All right. So if I had, all right. Is that clear? So I need to have 97.5% confidence intervals.
And that's squared.
The Bonferroni method.
95.
What?
So 97.5 squared is approximately 95.
Yeah, actually, we're not using independence here.
Okay.
We're using that. What we're using is the method uses the following: the probability of A and B. Okay. Is equal to the probability. Let's see, what is the formula? What's the general formula? The general formula is probability A union B equals PA plus PB minus PA intersect B. That's the inclusion-exclusion formula. Now let's turn it around. You get PA intersect B is equal to PA plus PB. Let's see, I put this thing outside, minus the probability of the union. Okay, so this is always greater than or equal to PA plus PB minus 1. Okay, because PA union B can never be bigger than 1. It's a probability. Okay, so minus 1 makes a lower number. Okay, that's the Bonferroni inequality. Does Bonferroni have two R's? I think it maybe has two R's and one N, right? I'm not Italian, so I don't know this stuff yet. Yeah, okay. Okay, so I thought. Okay, that's Bonferroni inequality. So I want two things to happen, right? I have, in the T method, I have the probability that beta 1 for example, is between beta 1 hat plus a t alpha over 2 nu, all right, standard error of beta 1 hat, okay, and greater than or equal to beta 1 hat minus t alpha over 2 nu, standard error of beta 1 hat. What's in the standard error of beta 1 hat is the sigma hat, right? And the SXX. Standard error of beta 1 hat is sigma hat divided by the square root of SXX. Okay. So that's a random variable. This is a random variable. Okay. The t is not a random thing. That's just a critical value. Okay. Or percentage point, we call that. Percentage point. It's a fixed percentage point. Something like that. Okay. So that's a random interval capturing beta 1, right? So, and if we actually give ourselves a beta 1 hat and a sigma hat, we don't know if that interval contains beta 1 or not, so we'd say beta 1's at home if it really is in the interval. But anyway, that's the 100 times 1 minus alpha percent confidence interval. Okay? Confidence interval when I actually plug in the numbers, right? So these, in this, guys, this is just sitting as a random variable. This random interval has probability 1 minus alpha. Okay, this interval has probability 1. That random interval contains beta 1 with probability 1 minus alpha. A particular instance of the interval, one choice of the random interval, contains, we don't know if it contains beta 1. We just call it a confidence interval, therefore, because we don't know if it does or doesn't. It's one pick from the hat. Right? You have a hat full of intervals. 100 times 1 minus alpha percent of them contain the beta 1, and I pick one interval at random from that hat. I call that the confidence interval. Okay, everybody with me now? But what I need now is to know that the joint confidence interval. Now I claim now that if I take two random intervals and then take the intersection of the events that they both contain, right? That's event A. Let's call this event A. And then have a corresponding event B that beta 0 is within its interval. Okay, event B I have is that beta 0 hat minus t alpha over 2 nu, standard error of beta 0 hat, less or equal to beta 0 less or equal to beta 0 hat plus t alpha over 2 nu, standard error of beta 0 hat. This event B also has probability 1 minus alpha under the normality assumptions in the simple linear regression model. Simple linear regression. That's all I'm doing here. Then, what it says is that events A and B simultaneously hold with probability at least PA plus BB minus 1, which would therefore be equal to 1 minus alpha plus 1 minus alpha minus 1 equals 1 minus 2 alpha. So simultaneously the events hold. So therefore I have simultaneous confidence intervals with confidence level 1 minus 2 alpha. So if I want confidence level 95%, I need to change the alpha to 0.025. Right? So I have to trim things down. So obviously you can do this with many events. Well, the Bonferroni inequality goes not only for 2 events, but for many events. So I can do A intersect B intersect C greater than PA plus BB plus PC minus 1. The derivation is a little harder, but you have that one as well. Okay? It's kind of intuitively clear. All right? So that's what I do. If I want simultaneous confidence intervals, I just adjust my alpha. That's one way to do. That's the Bonferroni method. There are other methods, but this is one method. Okay? Now, but on the other hand, last time we actually could talk about so I had simultaneous confidence intervals. What would that mean? That would mean that I'm showing where the pair is. I'm showing that the pair is between, let's see, if I say the beta 0 is between one interval, this is on the beta 0 axis, and then on the beta 1 axis, I've got in another interval, let's draw a picture here. I'm saying beta 0 is in this interval, with 95% or 97.5% confidence, let's say. Confidence. Okay. And then I've got, let's say, beta 1 in this interval with 97.5% confidence. Then together, beta 0 and beta 1 are in this little rectangle, right? With 95% confidence. Beta 0, comma, beta 1 belongs in here. Contains beta 0, beta 1. This is the membership sign backwards. Everybody following that? This rectangle contains beta 0, beta 1 with 95% confidence. Okay? So I actually have a region in 2 space in the beta 0, beta 1 plane. Okay? That contains the pair of parameters with 95% confidence. That's what it boils down to. Okay. Now, what a different method is to actually get an exact joint confidence region that's not a rectangle, but it's an ellipse. Okay, so that's another method using the fact that alternative methods. So alternatively, you can use the following joint confidence region for the pair. You use the fact that beta hat minus beta prime, x prime, x, beta hat minus beta. I'm not going to go through the calculations again. This is distributed as sigma squared times a chi-square of p degrees of freedom. Okay. I go through the calculation of the mean of this quantity in the notes for today, and then going back to the appendix and playing around, you can see what you need to do to get the distribution theory. I didn't go through the distribution theory in this class because we're kind of trying to do a graduate course at triple the rate of a normal graduate course. Okay. So I kind of skipped the distribution theory, which is in the appendices. Yeah, I have a little handout for it if you want. But basically, we'll actually go through more than his appendix. So I should hand that out to the graduate students. We need to be able to follow the appendix and some other stuff to be able to ascertain that this is indeed true. Okay. Anything involving the beta hat is automatically independent of sigma hat squared. That's also by the appendices. C.2.4 basically is one page that does all of this, except for maybe some calculation of expectations and so on, which I've been doing in the notes. This is true. It's independent of sigma hat squared. Okay. And so what you get is that what you have is therefore that beta hat well, I think I made a mistake in these notes, but because I forgot to divide by p. So you'll see this. Yeah, there's my P. Okay, on page 105. Okay, what you get is that beta hat minus beta prime x, beta hat minus beta, divided by P, okay, divided by sigma hat squared is therefore distributed as an F random variable of P and n minus P degrees of freedom. Okay. So what you can do is you can actually use this. What you get is a joint confidence region for beta. 0. Okay, beta equals, in this case, let's say for simple linear regression is just beta 0, beta 1 for simple linear regression, though this can be done in any number of dimensions. So let's just take 2 regression parameters to illustrate. That what you know, therefore, is that, therefore, the probability that beta hat minus beta prime x beta hat minus beta over p sigma hat squared, I forgot my p in the notes, okay, down there, less than or equal to f alpha p n minus p, that's the percentage point of the f statistic of p and n minus p degrees of freedom. This is equal to 1 minus alpha. Okay. So what this is actually a joint confidence region. What this defines is a joint confidence region for beta 0, beta 1. So the pair. What actually is, if I put in now a beta hat and a sigma hat squared, this is some kind of quadratic relationship in beta 0 and beta 1. So imagine in your mind's eye, if you can, or look on the bottom of page 105, if you can't, okay, where they actually do an example. They write this thing down. They actually put the beta 0 hat and the beta 1 hat. See if you can zoom in on this one. This is going to test your camera.
The picture of the ellipse is on the next page.
The picture of the ellipse is on the next page. But basically what they're doing is they're looking at this quadratic relation, and what you have is a beta 0 and a beta 1 as independent variables, but the beta 0 hat and the beta 1 hat have been plugged in. Okay. And so you get a quadratic relationship, which you can imagine is the equation of an ellipse. Okay. And so you get the inside of the ellipse as the joint confidence region for beta 0 and beta 1. Instead of a rectangle, you get an ellipse. But now it's an exact region. Okay. And if you want exact rectangles, then you have to take another method. Okay. So that's joint confidence intervals. So here I'll say is C appendix C.2.4 or something like that. Okay? and the notes. Okay. It would be fun to go through that distributional theory. It would take a day. Here. Heavy duty calculations, plus a little bit of probability review. So I'm going to skip it for now. If we have time later, we'll do so. Okay, we'll go back after we've seen all this other good stuff. Let's go on now. So that's really kind of an addendum to what we did last time, where we discussed a little bit about the distribution of these quadratic expressions. Saying that you basically have chi-squares or non-centered chi-squares coming out. Okay, the point was that this is a centered chi-square. Okay, because this was a centered normal. X times beta hat minus beta is centered. It doesn't mean 0, because it's a constant matrix times something. Beta hat was unbiased for beta, so that's a centered normal vector. And then if I take this expression, that's just a square of a centered normal. All right? So that means you're getting a chi-square with some kind of coefficient. And the only question is, whoops. Yeah, and the only question is how big of a chi-square, P. Okay, and so on. All right. Well, I know that's kind of over most people's heads at this point, so we'll just go on. What I'm going to do now is talk a little bit about extrapolation, because what people doing regression modeling have to consider is how good is the model, okay, in various regards. Does it fit the model well? Maybe, okay. But is it any good for extrapolating? In other words, or interpolating. In other words, if I wanted, okay, what does that mean? Okay, let's recall something about simple linear regression, which maybe you had in the beginning course or not. They kind of try to drill it into your head there. That if I have an XY plot in simple linear regression, and this is the scatter diagram, X and Y, just good old one X variable, one Y variable. Okay, then there's a certain range of the X values. Okay, and if you try to predict, and so you get a straight line here, let's say the prediction equation, okay, if you try to predict the value of y outside this x range, that's considered, to be flagged. Okay? You're doing extrapolation. Okay? Not prediction, because you have no data, x data in this region at all, or below this interval. Okay? So you have no idea. Maybe the straight line wasn't a straight line anymore. Really, maybe the data started to curve down, and you just didn't know that. Okay? If you would have plotted it. So you have no evidence in that region. So you just praying, okay, that I could extrapolate a bit. Okay? So how far can you extrapolate, and so on and so forth. So when you get to more than one regressor, then what we'll just do is show the picture of the regressors. Okay? So instead of having this interval, which was easy to plot, now what do I get then? Well, I can look at a scatter diagram of the two regressors, right? And then, of course, I could have the scatter diagram of all of the data, which would be in 3 dimensions, x1, x2, y. All right? So if I go to 2 regressors, then I'll try to draw a picture. Okay, let's just go ahead and rewrite this so that everybody has the same picture and on the same page. If I have 2 regressors and I put the 3-way scatter plot, x1, x2, y, then I get some points in space. So you're supposed to think of this as a cloud of points in 3 space, and then your regression modeling is to try to fit a plane to this cloud. Okay? So this is y hat equals beta 0 hat plus beta 1 hat x1 plus beta 2 hat x2. That's a plane. But then you have your x1 and x2 down here in the x-axis. So this is just x1 and x2. This is your x1, x2 plot. Okay, if I project all those points onto the x1, x2 plane, then that's your regressor space, your x space. Okay? X space is x1, x2 space. We're going to be kind of colloquial about that. We're not going to make up really great terminology, okay, in this text anyway. All right? So now, what does extrapolating mean? Does it mean extrapolating going outside the box that contains all of these points in x space, or does it mean going outside the smallest convex set that contains all of them, or what? So statisticians had to grapple with that. Now, instead of an interval, you've got something else. So then he talks a little bit about talking about the smallest convex set that contains all the points, the regressor variable hull. Reminds me of a math joke. Okay. So does that make sense? You take all those and that would be the region of, and if you take a point inside this, that will be called an interpolation point. You can also talk about the smallest ellipse, or you can not talk about the smallest ellipse, but then you can talk about other things. And then what he's going to refer to is something in the text as a certain ellipse that will contain the regressor variable hull. So sort of, this kind of a natural thing to do is to sort of associate some kind of ellipse with this thing. Okay. Ellipses are common in statistics because of the joint normal distribution. So I'm not going to say exactly what that, how that ellipse would be associated with this regressor variable hull. That's a non-trivial business. but we can talk about extrapolation versus interpolation. So let's say, what would be an extrapolation point? Yeah?
Can't we just eliminate this with a good design of experiment? I mean, we are picking x1 and x2.
Sometimes, yeah. Sometimes, but many times not. People will come to you with their data and say, help! Okay. Analyze this for me, would you? Actually, that's the easiest part about it in some ways. The design is kind of the hard part sometimes. But yeah, you're limited in certain cases. Take this delivery time data or what have you. They didn't design. Well, you're going to march 1,000 feet and take 25 cases to the place. It depends on what the situation was at the store that they had to stock this thing. So maybe those were fixed, and those stores are always the same, so it makes sense to fix the X1 and the X2. But what's the actual model in that universe of this umpteen number of sites where they have to stock the stuff? And if they build a new site, what could you expect for the delivery time? Now, would it be an extrapolation site, or would it be an interpolation site? See what I'm saying? No. You've got a new Home Depot, and you're going to have to take 60 cases of pop in there. Okay. All right. I think that was an extrapolation case, because I think 30 cases was the most in the delivery time data. All right. Is this answering your question?
Yeah.
Okay. All right, let's move on. So we're being a little bit we say that a new regressor vector x01, x02. Remember, I equals 0 means there's a new one. All right. Instead of n plus 1, we'll call it I equal to 0. All right? x03 up to x0k. So let's go to k regressors. We say that if this lies outside the regressor variable hull, or which is the smallest set we might consider to be the X space. Okay? That's the smallest thing we would consider to be the X spaces. I mean, you might make it even smaller. You might just say the X space is just these points themselves. Okay? But that's not reasonable. Okay? It's not very robust. Okay? So, if this lies outside RVH, then this vector of regressors, vector in X space, is an extrapolation point. Okay. Okay. And extrapolation is required to estimate the mean response. All right. Now here's a fact. Another fact which we're not going to be able to develop, but you may be able to believe. Okay? That if I take the vector 1, x1 up to xk. Now I'm not putting any second index on the x's, so this is just independent variables now, corresponding to the x1 and x2 axes here. Okay? That if I take this vector and I'm throwing in the 1, right, because I want a 1 by p vector, and if I take this times x prime x inverse, and then the column 1, x1 down to xk, and I consider the inequality of this less or equal to h max, where h max is equal to the maximum of the diagonal elements of the H matrix, where Hij is equal to capital H equal x prime x inverse x prime. That matrix. Okay? Look, this is just one row out of the X matrix. Okay? Alright, this is like one row out of the X matrix. This is like one column out of the x prime matrix, 1, x1 down to xk. So if I actually put an I in here, all right, then this would equal HII. Notice this, that HII is equal to 1 xi1 xi2 up to xik, and then x prime x inverse times 1 xi1 down to xik. That's how we've defined HII. It's a diagonal element, because this is the diagonal element of this projection matrix, H. Is everybody kind of following that?
And then, so if this is true, it's an interpolation?
If this is true, then that's the interpolation region, yeah. Okay. Let's see. Consider this. The set of x1 through xk. I have to put the 1 there, okay, but I'm only considering the set of x1 through xk in Rk, all right, in regressor space, okay, X space, such that, okay, then this inequality defines an ellipse that contains the regressive variable hull. This relation, what do we call this, star? I'll just call it star. Then this relation star defines an ellipse, ellipsoid, I guess I should call it in general, in Rk that contains the regressive variable hull. So it's some kind of ellipse like that, okay? Containing it. Now, should it be tangent somewhere? I imagine it does. Okay, where? But that there's kind of like the biggest HII will correspond there, right? So I guess I've made this the biggest one or something like that. Okay, where the HII is max at this point. Okay. Making sense? Kind of? It's believable, though it's not obvious that this should be maybe defining an ellipse. Without the 1, you can easily see it. And with the 1, you have to convince yourself. Okay? Because this is a positive definite matrix. Okay? A little bit of linearity. You have to do a little bit more work. Okay. So that's going to be our basic. We're going to expand the regressive variable hull to this ellipsoid. We call that our interpolation region, just because it's a lot easier to deal with. Okay? And so if I want to check any regressor values, x01 through x0k, check to see whether there's an extrapolation point or not, I just calculate this inner product with x1 through xk replaced by x0 through x01 through x0k, and put the 1s in there, and so on. So this is done. Okay, let's look at this in the example. Example 313, this has been done. Now, how do you calculate the HIIs and how do you calculate H max?
Just find H and then find the max of it.
Yeah, you find H, and I think I did it with the Maple program in the notes 3. I actually found the H matrix, and then it was easy. Once you find a matrix in Maple, you can easily call the diagonal elements, because you can call any elements. Now in Excel, I can calculate the H matrix, but how will I get the diagonal elements out? There might be a command in Excel. I was going to check it yesterday, like try mdiag or something like that. Just try some formula. Okay. Without looking at the documentation, I'm not sure if it can be done that easily, because it's going to be a diagonal array, not a column array or a row array, and Excel doesn't do too well with diagonals, probably, unless it's programmed. You could type it. You could pull the diagonal off. It's only 25 numbers. Okay, that's not so bad, but it's kind of crude.
It'd be easier just build your own.
You can eyeball it in most cases, because in most cases of interest, you could probably eyeball it and say, "I'll look down the diagonal," but you'd have to do something. So that's a minor annoyance. Perhaps. We haven't checked whether Excel can do it or not. All right? So, in the case of the delivery time data, then you have H max, it turns out to be, equal to 0.49829. All right? So you get an H matrix, and it looks like something, and the biggest number on the diagonal somewhere. And I'm not sure exactly which diagonal element was. I'd have to look back at notes 3 to check that. Here it is. I believe in the delivery time data there were 25 data points, and the diagonal matrix 1, 2, 3, 4, 5, 6, 7, 8. The 9th point. I guess that was the 30 cases and the 30 cases point. Okay, that was 0.4982. This was observation number 9. So this was the 9 element. And this is a 25 by 25 matrix. Okay, it was 0.4982. And I believe in the delivery time data, which is example 3.1, actually it was back in chapter 2. But 3.1 gives you both cases and distance. Observation 9 was 30 cases and 1,460 feet. That was pretty far out in the regressor space. Okay, it was like an isolated point way far away from all the other points. It was like a point way out here or something like that. I think there was a 29 cases as well. Or was there? Yeah, there was a 26 cases and 810 feet. But this was twice the distance. So it was kind of an isolated point. Actually, you have two. And I guess, let's see, with the 22nd observation had 26 cases and 810 feet, and the HII corresponding to that was 0.39. So you had 2 HII values. This is the 22nd observation. And all the others were pretty small. HII has to be less than or equal to 1. Because, let's see. Well, because I minus H is still a positive matrix, I guess. The identity minus H is still a non-negative matrix. So, non-negative definite. You can't have anything negative on the diagonal. That's one way to think about it. Okay. So I minus H is a non-negative definite matrix. And if you had a negative number on the diagonal, then it wouldn't be a non-negative matrix anymore. Okay, so HII is less than or equal to 1. Okay. So there's what it was, and that was the delivery time data. And so now let's put in something. I guess they asked us to say, let's take 8 cases and go 275 feet, all right, to deliver. Is that an extrapolation point? And then he goes ahead and calculates. And then let's see, how about if I had to do something else, and so on and so forth. So he takes, he takes 8 cases and goes 1,200 feet. All right, so there's a long gang way to go, all right? So it's not that big of a Home Depot, but there's a long way to walk. Okay? Somehow.
Everyone buys Coke, he's Pepsi.
Oh, well, that could be a problem. So I'm going to go ahead and calculate what I'm erasing here. I'm going to go ahead and calculate this for the case where I have, so if I take x1 equals to 8 and x2 is equal to 1,200 feet, this is 8 cases, at 1,200 feet, then I'll go ahead and calculate this product, this H00, I'll call it H00, equal 1, 8, 1,200. I have to calculate the x prime x matrix, inverted. We actually did that with Excel, almost. So we had the columns messed up. But you did that, right, Shane?
Yeah.
Okay. Does everybody know how to do inverses and all that? M inverse? And use the shift control enter key? Have you tried it yet?
I have one quick question about that. Is there any way that you can, does the data have to be like right next to each other, the columns for your X's, or is there any way you can pick a piece like this column over here and then this column over here to make your... No, you have to like just generate, you have to order them.
Yeah. Okay, let's just make sure we can do this. Let's go ahead and make this calculation on the board. Okay? Let's see, for the, I don't have the delivery time data, but, oh man, what should I do it for? I guess I can't. You don't have the delivery time data.
Well, we all do.
You do?
It's in the book.
Oh, I know, but I have to get the X matrix and it'll take a night and a day. Okay?
Right.
Is that website you can do?
Ah, the website. Okay. I'm with you. Let's do it.
Is this the first time that we've already sent?
If it's in there.
You can use someone.
Let's just go ahead. Let's go ahead through the... She's got the website. She's got the secret. Let's do it. Okay.
STP.
Yeah, I'm just gonna. It's linked to my website. Unfortunately, I had closed it, so I'm gonna have to go back to it. www.UCCS. You really want to see this? Okay. /G Morrow. Okay. All right, let's go. See if we can get there. Yeah, that was pretty quick. I guess it's not too bad. 483,583, and go to the website, please. Is the link working? How come it doesn't work? Can't you just, oh, you got to cut and paste it? Oh, it's doing it very slowly. Okay. Let's open up the website. Yeah, I'm sorry. Let's go ahead and do this. Open. Regress open. Okay. Do I really have to do this? Okay, let's see if it has delivery time data. Oh, it might not have it.
No, we just have to find the right problem.
It might have it under a different name.
Wording.
Yeah, we didn't have. There is no exercise because it's an example in the book. Soft drink. That's got to be it. Yes, indeed. Okay. There it is. Okay. So, do I need to save this as save as on the desktop or something like that? Okay. Now, is the other browser still open? So I have to close it or something?
Well, just minimize it.
Minimize it, but it won't let me open the one on the desktop. I'll have to close it. Yeah. Let's just close this whole thing. The browser's working all right. So what's the one I want? Data software. Okay, I got to close this one, right? That's the. No. Ah, what happened? It all died.
Just close it. Double click on it, it'll open.
Okay. All right, there we go. So here's the X matrix. This is the way that Shane taught us how to do it. You name it. Go here to the name box and you call it capital X, let's say. You have to hit the enter button in order to get it entered. Then the name goes in the center of the name box. You can't see the name box, can you?
You might want to include a row of ones.
I forgot. Okay, let's do it again.
So
I need to put that before.
Put it first, yeah.
So here's the question that Travis was having. Where do you put things? You just cut and paste so that you get it where you want it. I forgot. So I'm going to have to put 1 in here. Enter that, and then pull down the ones. Can you can read this?
Put 2 ones. Okay, never mind. It doesn't work that way. Normally it counts that way.
Okay.
It doesn't.
So now let's rename this. I don't know. Can I rewrite over a name?
You have to clear it. So you just call it something else. Call it like XT or something.
Okay. Let's just call it little x. Okay.
No, because Excel doesn't distinguish between the two.
It doesn't. Oh, that little double. Okay.
So you have to.
Let's call it W then.
Highlight it again. As soon as you clicked X, it went to what it was.
I know. I hate. Well, I could clear X, right? But let's not.
Let's call it W or something.
All right, W. All right. That's my W. Oh, I actually don't need it because I just need W prime W now, right?
Yep.
Okay, so I can call it whatever I want up here. All right, so I'll call it x prime x. So then I need to do an array formula. Right, it's going to be a 3 by 3. So it's equal to m mult. And then what we said was you can actually just put the arrays in. So even if I hadn't named it, I could do that, right?
Right.
All right, but since I did name it, we'll put it what? The transpose of W?
Yeah.
And there is no M transpose. That's just transpose. But make sure you have it spelled right. And then W, comma W. Then there is where you need to shift control enter, right?
Yeah.
Okay, so there's x prime x. Now I want the inverse of that. So now I need to put another 3 by 3. It's an array formula again. So first I have to highlight where it's going to go, and it has to be at least enough. And then go up here to the formula bar, and then put equal. Now it is an M inverse, M-I-N-V-E-R-S-E of. I could name x prime x, but it's easier just to highlight it. Okay. Close the parenthesis. Again, shift control enter. It's a 3-key sequence. Shift control enter in order to get it. Okay? And so there's my inverse. Now I need to calculate this business where I'm going to put in the row. Let's see. Let's put it, it was 1, 8, 1200, right? Okay. I already got H max, so I'm not going to calculate the H matrix now. All right? And let's see, I could reference this if you want. But let's not bother. Let's just put in... let's just do it this way, okay? So let's just take now, I need to highlight a space now before I'm going to get this scalar, all right? So I need to calculate that inner product, that scalar, and see if it's less than or equal to H max or not. All right, so that is equals M mult. It's a 3-way product, so I'm going to need 2 M mults. M mult, right? Because M mults takes 2 arguments. It takes.
I would use the other one that you used after you get 2 vectors, because
take this one, okay? That's the vector, and then times the x prime inverse x prime x, okay? Oh, really?
Yeah.
And then take comma transpose of this little dude. It's not going to like that?
I don't think so.
Shift control enter.
Oh,
All right. 1 minute to go. So 0.86736, that is indeed bigger than the H max, therefore you're at an extrapolation point. Okay. And so they showed a little picture. They took 4 examples. Let's see if you have 1 minute to show a close-up of the picture. I don't know, you have 30 seconds now. Page 112, where they show a picture of, they take 4 different scenarios. And the one we worked out was the X right here, the one at the top. And then they had some interpolation values and some extrapolation values included. Okay, so I think we'll call that for the first hour. And we'll go on to another topic next hour. Any comments? Okay. Very good.